Good afternoon, everyone. Welcome to the second week of special online course on hydrological modeling. And today we are going to discuss a specialized case which is very much common in the Himalayan region where we are located in Dehradun. And this includes how we can incorporate the melting of snow and melting of glacier ice in our hydrological models. So today we are going to discuss in this lecture today some fundamentals of snow hydrology and how we can use remote sensing for understanding, mapping and monitoring of the snow, and also combine the inputs from the remote sensing derived models and meteorological models for snow melt runoff modeling. The second part will include how we can incorporate the permanent ice, which is glaciers, in our hydrological models. And then there is a open source models which are available for the academic purpose and also for the operational purpose, which can be utilized for snow and glacier melt runoff modeling. And finally, what are the future advanced EO missions which will support these activities. So starting with the first one, so many of you or who are native of mountainous region and those who have come to the mountainous region in Himalaya as tourists in the winters, you might have seen the snow, which we call the solid form of precipitation. So in India, it is generally you will find the snow at elevations above 2000 meters, and this precipitation is generally happening when we have temperatures below 0 degrees Celsius. The precipitation will be snowfall. So in the monsoon also we are having this precipitation in areas about 2000 meters, but air temperature is higher. So as we will discuss in the lectures also, to snowfall to occur or snow melt to occur, generally 0 degree plus minus 1 to 2 degree is the temperature, critical temperature that we call, which is will be deciding whether precipitation will happen as a snowfall or it will happen as a rainfall. So this is the component which acts as a temporary storage, because once you have the heavy rainfall, immediately the runoff will start if the soil is saturated. But same is not the case with the snow. If there is a snowfall of the precipitation, then it will not be melting immediately. So depending upon the air temperature and incoming solar radiation, the melting from the snow can be delayed a few weeks to a few months in case of the mountain glaciers. So why it is important to study the snow and the glaciers? So if you see the headwater basins, when we say the headwater basins means the basins which are near to the source of these rivers, especially for the Himalaya, or in this case, example, the Western United States, or you can say European and Russian Alps. So those areas have very high dependence on the meltwater, and it can count up to 90% of the water supply for the growing population in various parts of the world. And this meltwater, once it is melting, it will be stored in terms of reservoirs. For example, the most famous reservoir or dam is Nangal Dam, which was created just after the independence. So the meltwater from the Satluj River comes, and it gets the hydropower also, and it is giving the agriculture or the water for irrigation to Rajasthan. So similarly, there are other environmental needs also which are satisfied by this meltwater. Then one more major thing is the flood prediction and flood protection. So if you remember 2013 floods of Uttarakhand, so that happened in the early part of the monsoon when the dams are almost empty or in the lowest level. So when the heavy rainfall happened, so all the flood wave coming from the Bhagirathi river was attenuated or sustained by the Tehri Dam, and only incoming flow was 7,500, but outflow was only 500. So they also act as a flood control measures. And sometimes the heavy snowfall in the springtime period, for example, in Jhelum River, or in the winter time period. So if there is a sudden increase in the temperature, that springtime snow can melt, and it can also lead to the flooding. It is this phenomena is very common in the areas, for example, in the high. So next is third component, which is very important from the global circulation models or the regional circulation models point of view, is the utilization of the snow and glacier feedback in the climate models. For example, our polar ice sheets and at the Antarctica and Arctic, and that sea ice, plus the seasonal snow cover during the maximum snow, the albedo of the snow is very high, so most of the energy will be radiated back. So thermal insulation can be provided by this one. So this insulation and energy feedback very important for the global circulation models in keeping the overall climate of the planet Earth under control. See the mountains. Himalayan River Basin, 35% of the jungle area is covered by the mountain. Out of this, 58% is conserving from the Himalayan River Basin. And in some of these Himalayan River Basin, the contribution of the snow and glacier melt is more than 50%. So you can see this particular figure where three big river basins like the Indus River Basin, Ganges River Basin, and the Brahmaputra River Basin, and some rivers also which are going to the mainland China and going to the this Eastern Asia. So they have their headwater basins which are covered with the seasonal snow here. You can see here, that is month of the February to March, and this one pink shade represents the permanent glaciers. So as we will see, the glacier melt peaks during June, July, and the snow melt generally starts to increase in spring time period, and maximum will be somewhere around May time period, and then it will reduce by the time of June. So this significant amount of water, the relative contribution of the snow melt and glacier melt is highest in Indus River, followed by Ganges and the Brahmaputra River. So you can see here the snow ice dominated average flows. So 64% of the India's water sources are represented by these three rivers, and they provide the water during the lean season. That means during the this March, April, May, June, when the other sources of water like the groundwater or other components, they are relatively less, because this is the time period when we get the pre-monsoon time period, when we get very less rainfall. And similarly, one more thing is hydropower. So this renewable energy is one of the major sources. So this renewable sources, majority is 25% is being contributed by the hydropower. So this is also a major factor, and this hydropower in the mountainous region is what we call the dependable flow, is contributed by the melting of snow and glacier ice. So this is just a representation from the analysis of remote sensing data, minimum and maximum snow cover area. This is Beas Basin. This is part of Indus Basin, but this is Beas Basin up to this particular location outlet. Thalot. So this maximum area of the covered with the snow will be 53%, and minimum will be 10 to 11%. And this is the Parvati Glacier, the biggest glacier in this particular river basin. This is Upper Ganga Basin. So you have this Gangotri Glacier here, Satopan Bhagirath Glacier here. So the maximum area will be 55%, and minimum snow will be approximately 14%. So this you can see the elevation here. So approximately up to 2,000 meters, the maximum snow cover will be there. So this will keep on fluctuating as the season will progress. Then third one is your Chenab Basin up to Aknur. So you can see Chenab Basin maximum snow cover area is approximately 74%, and minimum is 20%. If the minimum snow cover area is higher, that means it has larger number of glaciers. So starting from Barashigri, Samudra, Taku, and other glaciers in this basin. So they represent the permanent ice fields. There is Satluj Basin. Satluj Basin also have very high minimum snow cover area is 18% and maximum is 66%. So here this Bhakra Nangal is at the outlet of this particular river basin. So if you see the relative contribution of the melt, so it is the highest for the Chenab river basin 70%, and for the Satluj basin it is 60%, and for the Ganga river it is the minimum 30% at the Devprayag. So why we want to do the sensing based estimate of these parameters for the improvement? First reason is once we estimate the snow parameters or the land surface parameters which include soil moisture, they will be able to give us the spatial characterization of surface, so which will help us to improve our hydrological modeling. So this will be directly input to my hydrological model. The second is the hydrometeorological hazards. Snow avalanche is one of them. So this is the Manali South Portal tunnel here. So along this from Solang to Alundi area, so we have 10 avalanche sites. So these sites, in the winter, they will have very heavy snowfall, and this is the catchment area where this snowfall is being received. So these slopes are critical for avalanche initiation. That is, they are between 30 to 70 degree. And this slope, once the snow or depth increases by a certain critical threshold, and from remote sensing we can derive depth and density both. And once we add that to our simulation models, this is the runs model, so that can be used to simulate the how much snow will be accumulated at the road point. So those who are going to the Atal tunnel, so here there is a snow gallery. From the top of that gallery, avalanche will go. From the middle of the gallery, your vehicle passes, and from the bottom, in the monsoon season, the heavy rainfall induced this flash flood or the heavy water flow will flow. So these kind of applications are there, which are directly utilizing remote sensing derived snow cover and other parameters. So snow, if you see, is a microscopic view. If you see, this is typical hexagonal structure of the snow. So this is the field photograph of the Palchan area in Manali. So it is characterized by the basically three fundamental properties, which includes grain size, shape, and fabric, and there are the other derived properties which include density, porosity, and other parameters which are usually derived from microwave remote sensing data, and first one we can use the optical remote sensing data. So before we are going into the snow melt runoff modeling, because to do the snow melt runoff modeling, generally we require information on the snow cover area. So for the snow cover area, there are two approaches. One is optical remote sensing, and then second is the synthetic aperture radar or microwave remote sensing. So if it is a fresh snow, as I told, albedo is the incoming minus total outgoing minus incoming radiation. So this also reflectance here. So for the fresh snow, it can be as high as 0.92, and as it becomes firm, that means there is a lot of densification. Density is going above 0.4 grams per centimeter cube up to 0.6. Then you will have the reflectance reduction here, and albedo will be further reduced for the glacier ice. And in some photographs, we have the dirty glacier ice because they are in valleys, so there is a lot of weathering taking place, avalanches taking place, rockfall taking place. So in the bottom of the mountain valley, you generally find the glaciers to be covered with soil or mixture of soil and rock. So here the reflectance is almost as if it is coming from the soil. So if you increase the grain size, then the reflectance will decrease. So this 0.9 to 1 micrometer. So up to 1 micrometer, you see a distinctive dip. So this dip is generally used in hyperspectral data to estimate the grain size. And if you further go into the shortwave infrared or middle infrared, there is a distinctive absorption in the snow at 1.5 micrometer, 2 micrometer, and 2.4, 2.5 micrometer. So these indices which are used to map the snow cover area, they make utilization of this reduction in the this reflectance in the snow at 1.5 meter and very high reflectance in the green band. So the common parameter that we use indices is the normalized difference snow index. Similarly, if you want to map the snow throughout the year using the weather data, this radar data, then we can use the radar also. For the dry snow, we call it virtually transparent. That means the total backscatter is coming from the snow ground interface only. And if it is wet snow, then the majority will be coming from the snow volume and the snow surface, that is air snow interface. So this is true for frequencies from X band, C band up to L band. If you are going to the very high frequencies, that means wavelength will be smaller. In those cases, you may get volume scattering part, for example, KU band or the KA band. This is the schematic of the backscatter coming from the air snow interface if it is wet snow, ground and snow interface if it is dry snow, and volume if you have the high frequency. Otherwise, it will be negligible for the low frequency SAR data. So this is how you see a image of the radar data in HH polarization for the Gangotri Glacier. This is list for multispectral data, normal color composite. This is false color composite. This is normal color composite, where we have given the sphere band to the red, and for the green NIR, and for the blue we have used the red band. So in the SAR data also you can make the composite that we will see in the second part, where we studied the glacier mapping and glacier melt. So if you want to map the snow cover area, then as I told, we use the NDSI. This is an example of the MODIS, which is the most popular data because it can provide you the daily snow cover data, and it has two satellites at morning and afternoon pass. So you classify a pixel as a snow if the NDSI is greater than 4, and you add two more criteria. That means in the near the red band, reflectance should be more than 11%, and also in the if the band for reflectance is less than 10%, it will not be classified as a snow. That means the water pixels, because if you run this model, open water bodies will be classified as a snow because this NDSI will be greater than 4 for the open water body. So if you add this band 4 criteria, that reflectance greater than 11% and should not be less than 10%, then you can avoid water bodies being misclassified as snow pixels. Plus some thermal mask and impossible snow mask is also used, which removes certain pixels which may be found in the lower altitude or lower latitude regions. So same approach with certain modifications is used in ISRO's snow cover product that is available on Bhuvan every 15 days at 3 minutes. So this is not a global product, but for the Himalayan region, every 15 days using IIRS AWIPS data, you can derive this. And this is one example where we have combined the MODIS plus the data from our AWIPS. And then because even the MODIS is having very high repeat daily, and sometimes we tend to use the weekly product also. So sometimes in the peak winter it may happen, or in the monsoon, that the cloud is permanently there for entire week. So in that particular case, we have to use certain methods to remove the clouds. So generally most commonly used approach is to see 2 weeks before or 2 days before and 2 days or 2 weeks after the event, and make a long-term snow mask. So if one particular pixel in last 20 years is under the snow, and for example this particular week it is showing the cloud, so that long-term memory will be used to classify whether it is under the snow, or cloud is having the pixel is having snow under the cloud or not. So immediate, previous and after weeks data will also be used, and one long-term probability map can also be used. So this that has been derived, and it is minimum is 0.2 and maximum is going up to 0.67. and this is for 2016-17 when we had the excess snowfall as compared to the long-term mean. And then the second approach using the SAR data, you can use the snow cover mapping using the SAR data also every 24 days using the RISAT, our first radar remote sensing satellite for Bhagirathi basin up to Uttarkashi. This is for Beas basin up to Thakur. So now we have the operational satellite like the Sentinel. So you can see here, wet snow will have this darker appearance, the dry snow will have the this brighter appearance. So this Google Earth engine has been used in this particular study to map the snow cover as wet as well as a dry snow cover. So both data sets can be used. Then some advanced products has been estimated which are using the this scattering index kind of approach where we are utilizing the VV factor ratio of pH and VV to generate the snow depth map. And then, as I told, the spectrometer will have the highest sensitivity to the snow volume scattering. So that is being used in one of the studies where we utilize every 15 days change detection in the backscatter to estimate the change in SWE. So once we have the basic information from the satellites about the snow cover, or if you have some additional data on the density or the depth of the snow water current, next is the ground observation data. Because without ground observation data, we don't know whether the satellite derived data is correct or not. So these are some of the sites. For example, this is the snow depth sensor, this is the snow precipitation gauge. Then we have this snowpack analyzer, which measures all the parameters of the snow. So this snow water equivalent is the term that means snow depth multiplied by the density divided by water density, which is taken as 1. So if you melt a unit area and unit depth of water, and then you will get how much of liquid water, that is represented as SWE. So the snow melt runoff modeling is usually classified as a two approach. One is a temperature index approach and the second is the energy balance approach. So this is one example of the temperature index approach where we are estimating the snow melt by using the air temperature data as a primary input plus satellite derived snow cover also as one of the inputs. Then we have the runoff coefficient, degree day factor, and you have this temperature lapse rate and recession coefficients as the calibration, this other input parameters which can be calibrated to fine tune with the model. And once you are going for the energy balance, then we have to do the full energy balance. That means what is the total incoming radiation and outgoing radiation, which is function of albedo. Then we have to see the total incoming long wave radiation and outgoing long wave radiation, which is function of emissivity. Then we have to see the precipitation, how much rainfall, how much snowfall is there, whether it is adding the energy to the snowpack or removing it. Plus, we have to see the other turbulent fluxes, like what is the sensible and latent heat flux, and what is the ground heat flux. So all this energy, if you are able to balance, then net energy, if it is positive, that will melt the snowpack. If it is negative, it will freeze the snowpack. Now we will first see in detail the temperature index model. So this equation you have to see carefully. So this particular part, first part is the snow melt coming from the snow for a particular area. And here what we do, we have to divide our watershed in a elevation zones, because temperature is highly dependent upon the elevation as well as the this altitude. So here instead of dividing watershed into sub watershed, we divide into elevation zones. At each elevation zone, we should solve this particular equation. So once you have for a particular elevation zone, so this will be AN will be degraded. That means how much snow is going to melt in a particular day if you raise the temperature by 1 degree Celsius. So that is your degree day factor, and T is number of degree days for the duration for which temperature is above the critical temperature, and delta T is the temperature adjustment by the lapse rate. Generally, this value we take 6.5 degrees per kilometer, and this melt factor you can take this 4.5 to or 8.5 millimeters per degree Celsius, or 0.45 to 0.85 centimeters per degree Celsius per day. Then this SN is the ratio of snow covered area to the total basin area. Then the second part is your runoff coefficient due to the rainfall runoff, and this is the P is the total precipitation. Okay, and which is falling as a rainfall, not as a snowfall. And this is the conversion factor, because this Q is the discharge in meter cube per second, and here we are taking area as kilometer square. And K is the recession coefficient. This Qn is the discharge at time step just before the previous time step. So this Kn can be estimated from the observed discharge data, and then this can also be calibrated. So this particular model, if you want to do independent of any other model, that means you don't want to use the existing hydrological model, you are interested in only in snow melt. So Win SRM is the very popular model, which is freely available, Windows for snow melt runoff model. So this is the interface of this Windows SRM. So it will ask you the name of the basin, how many elevation zones you want to make, and then for each elevation zone, it will ask you the area, mean hypsometric elevation, its aspect, and the area in the particular aspect. And then in the basin simulation, you can define whether you want to do the distribution of temperature, precipitation, lapses by zone, or you want to do for the basin average values. So multiple simulations you can identify. The input parameters, what is required here is the lapse rate, the critical temperature, then you have this is the degree day factor, this is lapse rate, this is the runoff coefficient, and then one more factor is there, RCA. That means this factor, if it is 1, that means there is a positive energy which is being added into the snowpack. If it is 0, that means it is neutral, or negative energy is being added into the snowpack. Then other parameters are which are the input parameters. These are the variables which are changing, and these are the input meteorological parameters, like what is the T maximum, T minimum, T average temperature. CDC means conventional depletion curve. That is, depletion curve means ratio of snow cover area to the total area, and precipitation. So if you add the net radiation also, it will improve your simulation. Then it becomes the hybrid type of snow melt runoff model. So this is one example for the Manali watershed, where I am showing you this elevation zone map. These are the depletion curves, and these are runoff coefficient initial value you can take from the land use land cover. For example, if it is the rocky area, then runoff coefficient should be very high. If it is a snow, then also runoff coefficient is high. If it is the forested area, agriculture area, in those cases, your runoff coefficient is generally less. So this at each elevation zone, you have to do the zonal statistics to calculate the initial value of runoff. And this is the example of published work where we did this study in 2013-14. Where the snow melt runoff modeling was done using Win SRM for basin and Alaknanda basin. And this calibration validation was done using the observed data at Joshimath as well as at Uttarkashi. So if your air temperature data and snow cover data, if these two data sets are having very less bias, and for each altitude zone you are getting the good value, then your accuracy can be as high as 0.9 and above. But if, because my met station may be located at Joshimath, or maybe to this particular elevation where elevation is 3000, but my elevation of the basin, it may go up to 6000 meters or 7000 meters. So in that particular case, if your lapse rate is not taken correctly, then it may introduce the errors. So, and similarly, these peaks and dips, they may not match exactly. So that means your recession coefficient is not calibrated properly. So once you calibrate your recession coefficient and other parameters, then you can match it more accurately. So this model is very popular. because it requires the precipitation, snow cover area, and number of degree days. So this is the one study done by Emersil 2009, where they have used Moody's derived the snow cover and TRMM based precipitation. Both are derived from the satellite remote sensing only. And then some station data is there, graded station data, global data sets are available in CRU and then World Meteorological Organization. And from IMD also graded data is available. So degree days you can get from there. Although they may have all the input data have certain amount of errors, so they can be integrated into the SRM model, and you can get the snow melt runoff for entire Himalayan river basin. So this is the easiness of this model, which makes it very popular among the user community. The second category of the snow melt model is the variable infiltration, what we call the energy balance models, and very popular model which is freely available, and it is grid based. Most of the runoff processes or the hydrological processes what are happening physical based. So it considers grid based model. Each grid is partitioned into elevation bands, and for each elevation band the simulated energy mass fluxes are added, and area-based averages are done for the each particular pixel. So it considers the snow and three, just basically forms the ground snowpack, snow in the vegetation canopy, and then the snow at the top of lake ice. So it will have the various components, like how in the forested canopy it is melting is taking place, and how in the open area the melting is taking place. So basically, this is the fundamental equation for the snow melt runoff. So this is this what we call the energy balance of the surface layer, and it is considering the two-layer model. So in this one, energy exchange is taking place between atmosphere, forest canopy, and snowpack only at the surface layer. Okay, so the energy balance of the surface layer is represented by this equation. This W is the snow water equivalent, and TS is the temperature of the surface layer. So this rate of change with time is function of the QR, which is nothing but the net radiation. Net radiation means net incoming short wave and net incoming and outgoing long wave radiation. QS is sensible heat flux. Then this is the latent heat flux. QL, QP is the energy added or removed to the snowpack if it is precipitation as snowfall or rainfall. QM is the energy given to the snowpack if it is melting, or removed from the snowpack if it is melting, or given to the snowpack if it is freezing. So these are the basic fundamental equation, and within this there are terms which I have used. Sensible heat flux. So it represents the energy transfer between surface and air mass when there is a difference of temperature. So basically, this is the heat transfer due to the conduction. And that means it depends upon the temperature to be different at snow and the atmosphere. So if the snow temperature is higher as compared to the air, which can be a case when we have the fresh snowfall and suddenly there is no clouds. After the snowfall, there is a no clouds. In that case, there will be very less air temperature. So here it will be going into the atmosphere, sensible heat going into the atmosphere. And if the spring season is there, for example, during the daytime, clear sky and daytime is there, in that particular case, air temperature will be above 0 degrees Celsius, and the snow in the frozen state, it will be at 0 degrees Celsius. Then it is adding the net energy into this one. And both these sensible heat flux and turbulent heat flux are this latent heat flux are known as the turbulent fluxes. Why they are called turbulent fluxes? Because the exchange of heat is affected by the what is happening in the environment just below the snow surface. If it is windy, a lot of wind is taking place. In that case, there will be change in the energy transfer between these two. Otherwise, if it is a calm condition, there will be difference in the energy exchange. The second latent heat flux is the exchange of heat between the surface and energy due to the phase change. That means snow is melted into the water and going into the soil, or it can happen that snow is getting directly evaporated into the surface. That is sublimation is happening. So in that case, it will be decided upon the vapor pressure. If the atmosphere vapor pressure is lower as compared to on the surface, it will be adding the energy. If it is inverse, that means atmospheric vapor pressure is higher as compared to the surface, it will be adding the energy into the snowpack. So this is in terms of our energy balance. This is equivalent of our evapotranspiration, what happens in the normal areas which are not covered with the snow. Then if you have the rainfall, so during the snow rainfall, if you have this temperature below 0 degrees Celsius, it will happen as a snowfall. So it can add this, it will be total negative energy into the this one snowpack. If it is rainfall, it may add the positive energy into the snowpack. That is release of latent heat if rainfall is on the sub-zero snowpack, and sensible heat addition due to the heat added by volume to the relatively warm rain. Okay. Then similarly, there is a loss of latent heat during the melting process. Okay. So once it is 0 degrees Celsius and above that, the snow will starts to melt. It can go directly as a runoff, or it can saturate the soil and then it can go as a runoff. So once it reaches its liquid water holding capacity, which is generally taken as 10%. So 5 millimeter water within a snowpack of 50 millimeter SWE on the horizontal snowpack. So this is the condition when the melting is taking place. So to simulate the various criteria for the energy, because this energy balance model, it is not asking the user to provide the snow cover area. For example, in our temperature index models, if you see this particular equation, I am adding the snow cover area into the model itself. But when we are running the energy balance model, it is not asking for energy. It is just calculating at every time step the net energy. Okay. So once it is calculating the net energy and it is taking input as a precipitation and temperature from the user. With time, if there is a fresh snowfall or there is no snowfall but there is a compaction of the snow, so the snowpack will undergo metamorphism, compaction due to metamorphism and overburden pressure, which will change the density of the snow with time. Okay. So this density change affects the albedo, and once albedo is changed, your incoming shortwave radiation is and outgoing will be directly influenced. So you can use these some basic formulations which are implemented in the WIC model. So this albedo variation with time for the ablation season, and this is the albedo variation with this is the accumulation season. This is the ablation season. So that is function of snow density and the time since the last snowfall. So this model has a component for snow interception and canopy effects also. So the canopy interception is affected by the water equivalent which is getting intercepted, and it is function of my leaf area index. So leaf area index can also be derived from the remote sensing, and rest whatever is intercepted that will be retained up to the water holding capacity. Once the water holding capacity is reached, the rest water will fall as a through fall. So then one more major component in the mountainous region is the blowing snow, because one area you might say that actual snowfall is 1 feet only, but when you put the weather station or snow depth sensor there, you see 1.5 meter of the snow. So from where that snow has come? Or one area, it can reverse can also happen. 1 feet of snowfall as reported by the MET model or some other observation data, but actual snow depth is only 15 centimeters. So that means wind is transporting the snow from one place to another due to the topographical variation in the terrain. So that impacts our incoming shortwave radiation, and winds are attenuated through the canopy. So for that, we have the separate model. P is precipitation here, M is snow melt, Q is the sublimation from the blowing snow, Q is evaporation sublimation from the snowpack, and this spatial probability of occurrence of probability of the blowing snow. So this will be calculated by the input terrain data. So if you provide the standard deviation of terrain slope, standard deviation of terrain elevation, and auto correlation length, then it will be calculated automatically by the model. So these are the four model parameters which are used to calibrate minimum air temperature at which the snowfall occurs, minimum air temperature at which rainfall occurs, snow surface roughness, and value of M. So these are some of the locations and the input parameters where you can find this model and input data preparation. So this is the elevation band. This is the grid cell. For example, if it is 25 kilometers, you can see the subgrid variability in terms of land use, then the elevation variability within the single pixel, and then elevation variability is influencing my precipitation variability as well as my snow cover and temperature. So once you define the lapse rate, so for each elevation band, you will have the different air temperature. These are some of the input parameters that will be used in the elevation band file. So this is generally we do in the GIS in our department. We have our own now. Earlier it was on C++. Now it is on the Python and MATLAB. So these are some of the elevation files, elevation grid file, which is overlaid with the digital elevation model. And you can add this text file for each pixel. You need to make this kind of text file. And this is for the blowing snow. So if you have put the blowing snow as a true in global parameter file, you have to provide these three parameters. So once you run this model, for example, you run for the throughout the year, the model for each grid cell size will simulate snow water equivalent, snow depth, and snow cover. So this particular example is showing the basin area average for Devriyag, this Ganga basin up to Devriyag. So you can see here in the February, March, it is highest, and then it reduces. And by the end of June, it is almost zero. That means the seasonal snow has almost melted. Similarly, snow depth also, and this is the snow cover area. And this is for the snow and glacier melt for the entire Ganga basin to Stutti Ghat, Dev Ghat, and this is for Farakka. So this is the snow water equivalent and snow depth, and this is the seasonal contribution of snow melt to the runoff. So you can see here for the Joshimath or for the you can see here Farakka, the monsoon time period contribution of the snow and snow melt is almost near to zero. But if you see for the Dev Ghat or for the Joshimath, it is very high. And for this seasonal contribution is highest in the month of April and May, and then it will reduce as the monsoon will progress. Okay. So sometimes because it is not asking the user snow cover data, if there is a bias in the air temperature data. So whatever the precipitation it is being added, it will be added as a snowfall. So this is example of Bias Basin where the excess snow has been shown in the low elevation area of 800 meters. So in that case, special case, we have to make use of the data simulation. That then I run model not for the full year, but I run the model for 1 week. And then after 1 week, I assimilate the remote sensing derived snow cover area and force these pixels to this particular area that the snow cannot be beyond this. So with this, we can correct for the errors in the snow melt runoff model as we progress in the future. So this is the example where we have run this particular model for entire NWH. And you can see here, this is the snow depth calculated by VSC model with the ERA interim as a input forcing data. And you can see this particular precipitation band, particular elevation band between 1500 to 3500 meters, where we see the heavy snowfall and the seasonal variations in the snow depth. The second component of the lecture is the glacier melt runoff. So before going into the glacier melt runoff, we have to understand the various features of the glaciers. Like glacier is the flowing river of ice. So this is represented by the three distinct terms like the zone of accumulation, this is zone of ablation, and one hypothetical line which is known as the equilibrium line altitude. So this zone of accumulation will have the net addition of ice in a given glacier water year, and this ablation will have the net melting of ice in a given water year, which is generally we take from September to September in a particular year, August and so here, if the total ice addition of accumulation and ablation, if it is positive, that means it is adding ice into the total glacier system. If it is negative, that means there is a reduction in the total ice due to the melting or due to some other calving effect or other reduction in the ice. So this is the accumulation area, how it likes. If there is a warming climate, this ELA line will shift upwards, and if it is cooling time period, that means snowfall has increased, air temperature has decreased, then this ELA will go down. So for the typical Himalayan glacier, this line varies from 4,800 to 5,300. So this ablation area, equilibrium, there is a mass loss, and in the accumulation area, there is a mass gain. So this is a typical photograph, and these the older lines of the moraines, they represent the last glacier maximum. So up to 1850 or before that, this particular area or the glacier had the glacier ice up to this. Now it has melted. And the ice is seen only at this particular point. So this is my accumulation area here. This is my ablation area. So in the multispectral data, this is the multi-bands. You can see it as a grayscale. You can see sphere band here. The snow is seen as a less reflectance. Dave is covered as high reflectance. So if you combine this into the standard color composite, this is the Gangotri Glacier for the September month. So you can see supraglacial lakes here. These are the snow on the glacier ice, or we call this clean glacier ice also. And then these are the Chokhamba or the high accumulation area of the glaciers. So during the peak winter, you will see this entire area to be covered with the snow. So you won't be able to differentiate which one is glacier, which one is not. So only during the peak ablation season, which is August and September, you will be able to see such kind of data. So our purpose for this, how we can estimate this ice which is coming from the debris covered ice melting, then clean ice melting, and then there is a fern aquifer also. We call this fern region or the permanent ice here. So how we can estimate that? So these are some of the field photographs. You can see debris covered glacier here for the Buddha here. So this is the just below the snout where there is a avalanche has taken place. So you can see the surface temperature, land surface temperature is on the negative side as compared to the debris, which is adjacent to the this glacier where it is not underlain by the ice, so temperature is higher. So if you want to map, we can make use of the land surface temperature data. This is Mudal Tapu Glacier here. This is the accumulation region here, and this is the ablation region here. This is the proglacial lake here at the end of the glacier. This is the Gomukh in 2008 and 2014. And very remote sensing applications or the research papers you will find, or the government reports you will find, the retreat of the glaciers. The retreat represents there is a negative mass balance, and it is losing the ice at much faster rate as compared to it is being added, because glacier is moving river of ice. It is not that it is moving backwards, but if you focus on this point, it is moving forward only. This is the time-lapse image of Gangotri. This is Imda Glacier. This is Satupant. You can see here with each year it is moving forward only. But the net melting or breakage of ice at the snout is higher than the net addition of the snow in the upper catchment or the accumulation area. And if it is at the end, if you have the lake, so there has been well documented scientific research which shows if there is a lake, it will accelerate the melting of the glacier ice as compared to the area which is not having the glacier lake at the end of the glacier. So there are standard algorithms. So those who are interested in mapping, they can refer to the Global Land and Ice Mapping System (GLIMS) or what you can say the RGA inventory. So this is the overall flow chart where we use the threshold methods, some manual editing, and then some thermal data. Data also utilized. Some topographical factors are also utilized. So the most popular methods are the SWIR red NIR to SWIR ratio or red to SWIR ratio to map the clean ice glacier. And if you are using the mapping in debris covered glacier, then you have to use the topographical features derived from the digital elevation model and land surface temperature data to estimate the area of the glacier. So base data usually we take from the topographical sheets or historical maps, and the latest data we update using the remote sensing. So this is that same Imja glacier here in the Mount Everest region. This is the Khumbu ice fall. This is the Khumbu Glacier. So this is typical debris covered glacier where we use the combined use of topography plus land surface temperature to map this glacier. Once this is done, this is inventory. This is combination of RGA 5 and 6. So this global inventory data is available as a vector file. So I have focused here only on the high mountain Asia here, where you can see all our Indus, Brahmaputra, and Ganges basin and corresponding glaciers here. So once I know that particular these are the permanent glacier fields, so now I can further use this for the melt runoff. One augmentation you can do is using the synthetic aperture radar data to improve the existing maps because they will give you the access in the peak winters also. For example, this is Gangotri in the winter, this is Gangotri in the monsoon. So irrespective of the cloud cover or otherwise in the monsoon season or in the winter time period, I am able to see the various clean ice, debris covered ice and other features using the radar data. So this time series in the this is for the wet snow, this is for the dry snow. So in the wet snow, backscatter generally low. In the dry snow, backscatter will be generally high. So this kind of time series composites once we make, we can identify the dry snow zone, which is usually not found in Himalayan glaciers. Then we find the percolation zone, and then we can find percolation zone in the two and higher elevation and lower elevation. And then there is after that we have the wet snow zone with within the accumulation area here. Then there is a superimposed ice zone, which is also found here. And then after that, you have the ablation season or the clean ice. So using this, you can identify these features and the area boundary between this percolation or wet snow zone and the debris or this clean glacier ice is usually taken as the snow line elevation or the equilibrium line altitude. So we want to estimate the discharge coming from the glacier. So as I told, this is the snow in here and this is the glacier. So snow is also giving me the delayed flow. That means snowfall is happening in January, February, March. But this melt water is coming in April, May, and June. So it is storing the water, and then it is stored water is getting delayed response in terms of runoff when we are using the temperature index model or we are calculating the energy balance. Similarly, in case of glaciers also, this concept of storages was very nicely explained by this work by Jensen et al. In 2003. So where they identified three storages. One is the long-term storages, that means the glacier volume which will have the variation from month to century basis. So that is the permanent glacier ice here in this particular area. Then you have this snow, which is the seasonal snow cover, as I told in the previous this particular area here. So this is the glacier covered with the snow. So this is the seasonal snow. So as the snow melt will happen, the glacier will be exposed. Okay, and by the end of September or August, most of the seasonal snow has melted, and only the glacier ice is seen. So this is known as the intermediate storage. Okay. So this is the applicable to process and release of snow water from the glacier, snow and glacier on the seasonal scale. It affects the runoff in the glacierized catchments and the downstream rivers. Then you have the this also includes the water in the fern. So this is the fern area. So this firn area also release the water at the seasonal scale. Then you have the short term storage, which is generally found in the snow or the melting of the glacier water through the snow, fern, and glacial and subglacial pathways. So this is the anglacial. Anglacial means on the surface of the glacier, the meltwater is found, and you can find many channels. Then you have this subglacial and glacial parts where you find some moraines which are exposed on the surface, vertical kind of structures which are transporting the meltwater through the internal drainage system of the glacier, and then they are being joined by the bottom of the glacier to the finally to the stream system. Okay. So the supraglacial channels and ponds are also there, which you can see in the satellite data also, because they are open water bodies on the surface of the glacier, so they can also be identified. So they all represent the short-term storage. So all the diurnal variation, that means in the morning or in the evening, there is a difference in the discharge from the glacier melt. So that difference is generally due to this short-term storage. Now, this particular glacier is represented by the three parallel reservoirs. So when you want to simulate the glacier melt runoff, and then you can use a simple hydrological model where you use the recession coefficient differently for these three reservoirs. So Fern reservoir here, this is the Fern reservoir, will have the very long what we call storage coefficient, high storage coefficient. That means the melt water from this, it will take longer time to reach to the, you have the snow reservoir and the ice reservoir. So ice reservoir represent the clean ice, snow is the intermediate between the fern and the snow. So for simplicity, in this work, they have decided that this fern area is constant, but this snow and ice is inversely proportional. As the snow reservoir will increase, that means that is at the start of the winter, the spring, your exposed ice is minimum. So in that case, snow reservoir is higher. As the seasonal snow will start melting, this ice reservoir will be exposed up to this maximum. So you can see here various components for the recession coefficient, storage coefficient for the fern 350 hours, for the snow 30 hours, for the ice it is 16 hours. So you can see here at the melting season, you can see here initially snow component is higher, and once the snow has melted away, you can see here ice component starts to increase. So the melt from the ice is increasing, and this is the fern component. So fern is from the previous, so that is also increasing maximum during the ablation time period, and then starts to decrease, and this is the measured discharge. So this kind of models I will show at the end of the slides. They are now available as the open source modules. So this is from the observation data which they did in the Svalbard region. So apart from this, there are some existing models, very popular hydrological models, which are used for the rainfall runoff modeling and other purposes. For example, SWATR model is the soil and water assessment tool. So this model has been used, has been updated with the temperature index based snow melt runoff model. So here rate of change of water equivalent, there are 5 steps. In the first step, you see the ratio of meltwater which is getting frozen, or it is getting sublimated in terms of water going from ice to the water vapor stage. Then there is a degree day factor for the melt. So this degree day factor is the function of the time of the year and the duration for which it is there. So that is also part of the calibration. Then the ice snow sublimation or the evaporation, that is calculated based on the Penman-Monte method. And then for the actual sublimation and the evaporation of the ice or snow, the albedo or what we call the sublimation evaporation constant coefficient for the ice will be used, and it will be changed with the season. Okay. So this is the equilibrium factor for 21st June, and this is for the 21st December. That means what is the maximum and the minimum. Then turnover of snow to ice as a ratio of water dependent of the snow or ice. So this is the water equivalent of snow or ice. Beta is accumulation constant, and it will assume to be changing with the season. So this will change with the season. And once you have exposed your glacier melt model, it will increase or decrease the glacier volume. Okay, so that the area change in the glacier will be with respect to this particular formulation, and the volume of the glacier change or the volume of the glacier will be estimated using this water equivalent, which is calculated from the previous time step, and using the area of the glacier, which is calculated from this, and this is the density of the snow. So you can see here this total watershed area is divided into the two parts: snow area and glacier area. So this glacier area, initially you have to give the glimpse-based boundary for the glacier. So on the glacier, there are also two conditions. Here the melt can take place only from the glacier ice, or glacier ice is covered with the snow. So in this particular case, there will be a separate module for the melting. So this is implemented into the and this variation in the snow and this glacier, it will keep on changing with the time step. So this will be ice will be maximum during the August, and this snow will be maximum during the month of March. The second category comes under the energy balance model, WIC model only. So here what we are doing, we are calculating the glacier temperature using the base temperature data and the elevation of the glacier. So apart from the elevation grids, you have to define the elevation grids with the glacier boundaries. So you have to define that within the grid, how much area is covered with the glacier ice and how much is not covered with the glacier ice. And once you calculate this, you have to calculate the mass balance of the glacier using this equation, where this Qm is the glacial surface energy balance, which is function of net radiation, sensible heat flux, latent heat flux, radiation due to rainfall, radiation due to the ground heat flux. So net radiation is function of the albedo here. So for this albedo for the glacier, it is taken constant. This is 0.34, and it is the function of air temperature. Okay. But if you take the overall albedo, which is function of my snow albedo here and the glacier albedo, and it is also function of the what do you say here, snow water equivalent from the snow accumulation and melt over the snow ice using the WIC model, which we discussed previously. And D star is the scale length for the melt water equivalent, and which is for the 24 millimeters. So the incoming short wave and outgoing long wave short wave radiation is function of the surface albedo only. So directly you can calculate. For the long wave radiation incoming, it is being calculated as a function of cloud cover here, and also it is function of my emissivity. Okay, and this emissivity is function of my vapor pressure, and outgoing long wave radiation is function of emissivity and the temperature. Similarly, this sensible heat flux QH and QL, it is the function of the roughness length as well as the stability functions for snow or for the ice and for the air. So this stability function plus the wind velocity. So the once this is calculated, the energy due to the rainfall, it is the function of my total rainfall rate and the difference in the temperature of the precipitation and the surface temperature when the rain leaves the glacier surface. And the ground heat flux is generally taken, maximum is taken as 5 watts per meter square. And it varies between 5 to 0. Between 1st July it is maximum, and by 1st September the snowfall will start. It is considered as 0. This particular glacier melt model was used in Uttarkashi, up to Uttarkashi for the Ganga basin. So you can see here for the Uttarkashi, the glacier melt contribution is 15%, snow melt is 27%, and rainfall runoff is 57.7%. So this contribution of glacier melt, it will increase and go near the Gomukh area. So here Gomukh area, the glacier melt can be as high as 40%. So one more simpler model which has been reported for this Chota Shigri Glacier in literature is using the simpler model, which is a function of degree day factor. So this degree day factor, you can take this degree day factor separately for snow or for ice and for the debris covered ice. So this is actually not 334, this is 3.34. So this is 3.34. So once you calculate this melt temperature, threshold temperature, which is usually taken as the 0 degree Celsius, then only this melting will take place, and the snow melt coming from the glacier surface and non-glacier surface. So because in the winter, this entire area is covered with the snow. As the melt is progressing, this is becoming snow free. So melting of the snow is taking place on the glacier and outside the glacier. So this is that component. Then you have the rainfall runoff, or rainfall can happen also on the glacier and also on the non-glacier side. So the total glacier is taken as snow, melting from snow, from the ice, and from the rainfall. So you can see here, this is the total runoff here, green representing the snow melt component, this red representing the ice melt, and the blue representing the rainfall runoff. So because this outlet is very near to the glacier, here the relative contribution of rainfall runoff is very less. It is dominated by snow melt and the ice melt. But if you take the same particular basin, for example, in Uttarkashi here 57%, because here we are much farther away from the permanent glaciers here at Uttarkashi. Higher you go in the river catchment, relative contribution of snow melt and glacier melt will increase. Now, in the literature, there are more open source models also. This is one example where user can itself make the data. You can utilize the data from the nearby weather stations to calculate the degree day factor, and other factors you can calculate from the remote sensing the snow cover area or the weather station data which is available near the glacier. So if you do not have this particular data, then the three models are available in the literature. This is distributed energy balance model, distributed enhanced temperature index model. So the traditional temperature index model makes use of the degree days only without considering the influence of the clear sky incoming solar radiation. So if you make use of the clear sky incoming solar radiation at the snow or the ice surface, you can see spatially distributed this particular map. So this will have the much higher accuracy as compared to the traditional model, which is only function of degree day factor. Okay, so this is that DTM model, and you can use this website to download this. Then one more model is there which is available in Python. So SPY, spatial process, is hydrology model, and it's a GUI is also available in the QGIS. Then there is a one more model, open glacier model, which has this COSIPY, which is function of the COSIMA model, coupled snowpack and ice surface energy balance and mass balance model. So this is also COSIPY is available on this website. So apart from our temperature index model, which is implemented in SWAT model or HMS model or Orbic model, which is the energy balance model, so there is a specialized snow glacier modules available in those models. So you can use these three models also for your purpose, or if, for example, you want to use the existing weather station data and some observation data, you can make the simpler cases of the snow melt and glacier melt also using the basic degree day approach. So what remote sensing can offer you? Remote sensing can offer in the last week you must have known that there are multiple layers. Most common layers for hydrological modeling are land use, land cover, your digital elevation model, and the input precipitation data. So for this, to better characterization of the glacial surface, how fast they are moving, or how their volume changes are happening, or height changes are happening. So two missions, NASA ISRO SAR mission, and then there is a crystal Copernicus polar ice and snow topography altimeter, which will give you the interferometric radar-based height values for the ice sheets and the glaciers, and this will give you the precise value of the movement of the glaciers, plus it will also give you the experimental output in form of snow density and snow depth, which can be used to see the efficiency and accuracy of our hydrological models. So with this, I complete my lecture, and if you have the questions, you can ask now.